Yeah, sharing my screen. Today I will explain you how to design this all gates by using MUX, and also will write. So I'll explain you the how to write the Verilog code for this all gates using MUX, 2x1 MUX, and also after that I will explain. In this parallelly, I will explain that in that only for AND gate, if you take AND gate, is buffer is possible or not, or inverter is possible or not, that I will explain. Okay, for that I will explain the code also. Okay, so screen is visible now. Give response. Okay, okay then. Okay, yes. So here, if you see, so all gates means how many gates you have. So all gates means, I think my screen is visible. Okay, okay. So all gates, so if you see, you have like NOT gate. Okay, 1 second. So you have NOT gate. Okay, NOT gate. Okay, first NOT gate. Okay, so NOT gate I want to implement with 2x1 MUX. How to implement with 2x1 MUX? So you know the truth table for NOT gate. So this is A and this is Y. Okay, 0 means 1 and 1 means 0 you are getting. Okay, Y equal to what? A bar. Okay, so this is my basic NOT gate. Okay, inverter. Okay, this is nothing but inverter. So how you are designing? Just here this is 2x1 MUX. So here what you are doing, here selection line is A. Okay, and here you are giving the output 1 and here you are giving the output 0 and Y. Okay, so you know the Shannon's equation. Y equal to, what is the Shannon's equation for 2x1 MUX? So 2x1 MUX, you have S bar I naught plus S into I1. Okay, so this if you substitute, you are getting A bar and 1 plus A and 0. Okay, so this is Y equal to what? A bar plus 0. This is equal to A bar. Okay, so this is the NOT gate. Okay, and 2x1 MUX. Okay, this is 2x1 MUX. And next, if you see the buffer. Okay, how to design the buffer? So this is the buffer. Buffer means what? Whatever the input you are giving, you are getting the output. Okay, that is nothing but buffer. So here A and output is Y. Okay, 0 means 0, 1 means 1 you are getting. Okay, so here same thing. So whatever the outputs are there, you need to give. Okay, so 0 and 1, and this is A. Okay, and 2x1 MUX. Okay, if you write the Shannon's equation, A bar and 0 plus A and 1, so Y equal to what? A. You got the buffer, Y equal to A. Okay, so like this you need to design the buffer by using 2x1 MUX. Okay, so I designed the NOT gate and buffer. Okay, and next I need to design the AND gate. Okay, how you will get the AND gate? Okay, so how you will get the AND gate? First AND gate. So if you see the AND gate, okay, first you so this is the symbol for AND gate. Okay, so this is A and B. Y equal to what? A and B. Okay, Y equal to A and B. So first you write the truth table, A, B, and output is Y. Okay, output is Y. 0 0 0 1 1 0 1 1. Okay, so in divide two equal parts. Okay, so that means here this A is 0 and A is 1. Okay, so A is 0, both times this is 0 and this is 1. So I can make A as selection line. A as what? Selection line. Okay, and B as input. Okay, I need to consider B as input. Okay, so here what I can do? See here. So that means what is the means how you will define the AND gate? If any input is low, the output is low. Both inputs are high, the output is high. Okay, so here I naught equal to what? I naught equal to 0 and I1 equal to, it is following B, so this is B. Okay, so from this you can design the MUX. Okay, 2x1 MUX. So MUX is a universal circuit. That means you can design any of the circuit, any of the gate by using MUX. Okay, that's why we call as MUX as a universal circuit. Okay, this is 0 and this is B, and Y equal to what? A you are giving a selection line. So if you see the Shannon's equation, A bar and 0, A and B. Okay, so this means this is Y equal to what? 0 plus AB. So Y equal to what? AB. You got the expression, no? So this is the AND gate. Okay, now my next here itself I am telling whether so by using AND gate, can we, so I have like a buffer and an inverter in my pocket. Can I design a buffer or inverter by using AND gate? Okay, I can see here. So inverter is not possible. So if you see the truth table, you are getting 0, but buffer is possible. You are getting B, no? Buffer is possible. How it is possible? So buffer, this is the buffer. So you are giving A, you are getting A. Okay, so that means one thing is inputs tied together. So this is A and A. So this you are getting A. Okay, so this is nothing but buffer I can design. Okay, or otherwise one more representation. This is A and one input if you are giving with 1. So this is A and 1. This is equal to what? A. Okay, so like this. So buffer is possible. That means by using AND gate, buffer is possible, but inverter is not possible. Inverter is not possible. Okay, so this is AND gate. Okay, and next, so this is the AND gate. Next, OR gate. OR gate, how you need to design OR gate? So if you see the OR gate, first you draw the just diagram for the OR gate. This is the diagram for the OR gate. This is A, B, Y equal to what? ARB. Y equal to ARB. So just write the truth table A, B, and output Y. Output Y. Okay, 0, 0, 0, 1, 1, 0, 1, 1. Okay, so how we will define the OR gate? If any one of the input is high, the output is high. Both inputs are low, the output is low. Okay, from here what is I naught? I naught, it is following B, so that means this is B, and I1 equal to what? 1. Okay, I1 equal to 1. So from this I can design the 2x1 MUX. So this is B, and this one is 1, and output is Y, and this is selection line. Anyway, these both are zeros, means I need to consider A as what? Selection line. Okay, so here if you see the Shannon's equation, A bar and B plus A and 1. Okay, so you got this is nothing but A plus A bar B. You have absorption law in Boolean algebra. A plus A bar B. Okay, A plus A bar B, this is equal to what? ARB. This is the redundant. Okay, so that from that you can write as what? A plus B, ARB. Okay, you got the expression, ARB. And now now here OR gate also. So OR gate, buffer is possible. Buffer is possible. Why? Because you got B, no? You got B. Buffer is possible, but inverter is not possible. Inverter is not possible. So how you will design buffer? So see here, buffer I can design like this. See here, like suppose inputs are tied together. I am giving to OR gate. So this is A, and A or A. What you are getting? A. Okay, A or A. What you are getting? A. So buffer I will get. Okay, when inputs are tied together, I will get A. Okay, and next you see. Next, I can give like this also. This is OR gate. OR gate. This is A followed by I am giving to 0. So this is what? AR 0. This is equal to what? A. Okay, AR 0 equal to A. Okay, so like buffer is possible, but inverter is not possible. Okay, so this is about OR gate, and next we'll see the NAND gate. Okay, NAND gate. So what is the NAND gate? We'll see. Okay, NAND gate. I think we realized the NAND gate. No, NAND gate by using inverter and all gates. Okay, NAND gate is a universal gate. So first this is the NAND gate. This is the NAND gate. So this is A, B, Y equal to what? AB bar. Y equal to AB bar. So just you write the truth table. A, B, and output is what? Y. Okay, so how we will define the NAND gate? Just opposite of AND gate is nothing but NAND gate. Any one of the input is low, the output is high, or output is low. Okay, just this one you see. So here I naught equal to what? 1. Okay, and I1 equal to B bar. Here B is 0 1, Y is nothing but 1 0. So this is B bar. Okay, anyway this is 0 0 means A is selection line. A is what? Selection line. Okay, so here you see 1 second. Okay, okay, so here what you can do, so just you design 2x1 MUX. So what is I naught? I naught is 1, and I1 is B bar, and this is Y. Okay, so A is the selection line. So just write the Shannon's equation: A bar and 1 plus A and B bar. Okay, A and B bar. So again what you can do, so here so here this is same like a absorption law. This is A bar plus AB bar equal to what? A bar plus B bar. A bar plus B bar. Okay, that this is the redundant. Okay, so you can write A bar plus B bar. Okay, you have a De Morgan's law. What is this? AB bar equal to what? A bar plus B bar. So I am applying De Morgan's law. You will get what? AB bar. AB bar. So this is NAND gate. This is NAND gate. Okay, now my next question is what? So I have a buffer and inverter. So is this NAND gate is acting as a buffer or inverter? Okay, now buffer. Okay, B is not there in this table, so buffer is not possible. Inverter is possible. Why? Because you have B bar, no? So inverter is possible. Okay, inverter is possible. How it is possible? When inputs are tied together. When inputs are tied together, so you see here A and A whole bar. This is equal to what? A bar. Okay, inverter is possible. Okay, and next one more representation is there. This is representation 1. Second representation is, this is inverter A, and other input you give it to logic 1. Okay, other input you give it to logic 1. So when you give it to logic 1, what you are getting? So here you are getting A and 1 whole bar. This is equal to what? A bar. A and 1 whole bar equal to A bar. So like this we can implement NAND gate by using we can have the inverter. Okay, we can have the inverter. Okay, and next NOR gate. Okay, NOR gate. So how to define this NOR gate by using 2x1 MUX? So if you see the NOR gate, so NOR gate is also called as a universal gate. You can get the any of the gate by using NOR gate. So just draw the truth table for NOR gate. So this is the truth, this is the logic diagram for NOR gate. So Y equal to ARB whole bar. This is the NOR gate. So now just write the truth table for NOR gate. Just OR gate followed by the inverter is nothing but NOR gate, no? So 0 0 0 1 1 0 1 1. Okay, so how we will define the NOR gate in one statement? If any one of the input is high, the output is low. Output is low. Okay, here output is 1. Okay, so from here you can say that what is I naught? I naught equal to B bar. Anyway, this is selection line. A is the selection line, and here I1 equal to what? I1 equal to 0. Okay, so you draw the MUX, 2x1 MUX. 2x1 MUX. So this is B bar and 0, and this is I naught. This is 0. Okay, so this is Y. Okay, so Y equal to what? One second. Yes. Okay. So here what you are getting? This is selection line A. So A bar, B bar, A bar, B bar, A and 0. Okay, so this you are getting as what? A bar, B bar plus 0. So this is equal to A bar, B bar. Okay, from De Morgan's law you know that A or B whole bar equal to what? A bar, B bar. Okay, so this you can write as what? A or B whole bar. A or B whole bar. Okay, so NOR gate. Okay, so again next question is what? Buffer is possible or inverter is possible? From the table itself you can say. So from the table, buffer is not possible. Why? Because B is not there. Okay, inverter is possible. B bar you have, no? B bar you have. Inverter is possible. How it is possible? So that means so when inputs are tied together and you give it to NOR gate, okay, you are getting what A whole bar, this is equal to A bar. Okay, this is one representation. Other representation is uh, NOR gate. NOR gate, this is A. Another input you need to give it to 0. Okay, this is A or 0 whole bar, this is equal to A bar. Okay, so this is NOR gate. So buffer is not possible, but inverter is possible. Okay, inverter is possible. Okay, this is NOR gate. Okay, and next we will see the XOR gate and XNOR gate. Okay, so XOR gate is nothing but odd detector. For odd number of inputs you have the output as 1. For so this is the logic diagram for XOR gate. Okay, XOR gate. XOR gate. Okay, so this is A, B, y equal to what? A XOR B. What is the expression? A bar B plus AB bar. This is the expression. Okay, y equal to A bar B plus AB bar. Okay, just you write the truth table A, B, and output Y. Okay, output Y 0 0 0 1 1 0 1 1. Okay, so just for odd number of inputs, odd number of ones, output is 1. And even number of inputs, same inputs, output is 0. Okay, so from here this is anyway selection line, and this one you see. So I naught equal to what? I naught equal to B, and I1 equal to B bar. I1 equal to B bar. So I can draw the 2 cross 1 mux. This is 2 cross 1 mux. Okay, and this is B, and this is B bar, and I am giving to A and Y. Okay, just write the Shannon's equation A bar B plus AB bar. Okay, so Y equal to what? A XOR B. Y equal to A XOR B. This is XOR operation. Okay, and next if you see the XNOR operation. Okay, now if the buffer is possible or not. Okay, so my next question is buffer is possible or inverter is possible. Buffer is possible and inverter is possible by using XNOR gate. Why? Because you got B, so buffer is possible. You got B bar, inverter is possible. Okay, how the buffer is possible? Just this is XNOR gate. XNOR gate, you give one input, other input you give it to 0. Okay, A XOR 0. Okay, so what is A XOR B? A bar B plus AB bar, no? A bar and 0 plus A and 1. Okay, so this is 0 plus A. What you are getting? A. Buffer is possible. Okay, so this is buffer. Okay, and inverter, if you see inverter, XOR gate A, and here you give it to one more input is 1. Okay, A XOR 1 equal to what? A bar and 1 plus A and 0. Okay, this is A bar or 0, this is equal to A bar. Inverter is possible. Okay, so this is XOR gate. Okay, XOR gate, and next XNOR gate we'll see. Okay, XNOR gate, how to design this XNOR gate by using 2 cross 1 mux, and whether buffer or inverter is possible or not. Okay, so just draw the logic diagram. So this is the XOR is nothing but so XOR followed by an inverter is nothing but XNOR. Okay, so this is A XNOR B. This is equal to what? A XOR B whole bar. So this you can write as what? A bar B bar plus AB. This is the expression for XNOR gate. Okay, so just you draw the truth table A B. Okay, this is event detector for or equality operator. We can call as equality operator. Okay, in the comparator you will get the XNOR only for the A equal to B. Okay, equality operator means what? Both inputs are same, you will get the output as high. Okay, different means output is low. Okay, so just you divide I naught equal to what? I naught equal to B bar you are getting, and I1 equal to B you are getting. Okay, so So you can design with 2 cross 1 mux. So 2 cross 1 mux. So this is B bar, B, and this is A. Okay, and write the Shannon's equation: A bar, B bar plus AB. A bar B bar plus AB. This is nothing but A XNOR B. Okay, A XNOR B. Now next, what is my question? Buffer is possible. Buffer is possible. Why? Because B you got. Inverter is possible. Can we design the inverter by using this XNOR? Possible. Both are possible. Okay. So both are possible. And next, so how to design this? So we can design this. Suppose XNOR is there, no? So XNOR, how to design? Suppose if it is a buffer. So just this is XNOR gate A, and another input you give it to 1. Okay, so if you define this one, A bar and 1 plus A bar 1 bar plus A and 1 bar is A and 1 second, A bar and A bar 1 bar, A bar B bar. If it is 0, okay, A bar 0 bar, 0 bar, and A and 0, okay, A and 0, okay, AB. So that means A bar and 1 plus 0. So you are getting inverter. Okay, this is nothing but inverter. Okay, inverter is possible. So if it is buffer, just you design A with 1. Okay, A bar and 1 bar plus A and 1. Okay, A bar and 0 plus A. Okay, so this is 0 plus A. Buffer is possible. Both buffer and inverter is possible with the help of XOR and XNOR. Okay, so this is the realization of this whatever the all gates by using all gates by using 2 cross 1 mux. Okay, 2 cross 1 mux. This I want to realize. Okay, this I want to realize by using Verilog code. Okay, so I wrote the Verilog code. Just I will explain the Verilog code and test bench. Just you see. 1 second. All gates using mux. So all gates using mux, I wrote RTL, SIM and TB. Okay, so this is RTL. Okay, I wrote in GVim. Okay, GVim is a powerful text editor. Some commands will be there. So most of the industry they will use this GVim only. So better to practice the commands in the GVim. Okay, and this GVim only I am using in the Costa Sim. Okay, so see here. First what I did, module gate, this is a module, and module name or identifier is nothing but gates using mux, and input wire A and B. Okay, output wire AND gate, OR gate, XOR gate, NAND gate, NOR gate, XNOR gate. Okay, here I use the concept called functions. Okay, functions is nothing but what? Every time functions is nothing but it's like a C only. Every time, suppose if you want to call, okay, so every time you are writing same program, suppose you have like 5 lines of code, so you want to write that 5 lines of code 10 times. Okay, so 10 times 5 lines of code means 50 lines of code you need to write. Okay, so that means it will be code will be very complex, and so time consuming will be there. So in that situation you can use you can use the function concept. Okay, function is nothing but you can call that function. Okay, function you can call with arguments. Okay, those are nothing but function have some arguments. Okay, we can it will return some value. Okay, function will return some value, but function doesn't have the delays, but task have the delays. Okay, task is same as the function only. So here I wrote the function like for the 2 cross 1 function mux2. Okay, input select d0 d1 begin, and I am using ternary operator. So what is my ternary operator? Or this is one ternary with one condition I used. Okay, so mux2 equal to if selection which is connected d1. Okay, if selection line equal to 1, d1 is connected. If selection line equal to 0, d0 is connected. End and end function. So this is my function. Okay, after that what I did, I wrote for the AND gate. Okay, AND gate, for AND gate So assign, so AND gate, AND underscore gate, MUX to. So for AND gate, what I got, see here. For AND gate, we see here on AND gate. AND gate, I not equal to 0, I1 equal to B I got. Okay. So same thing, see here. So I'm calling this function I not equal to A and I1, this is, what we got, one second. I not equal to 0 and I1 equal to B, no. So first I1 will come. Okay. I1 will come. So first A, that is D1. Here D1. Okay. And next one tick binary 0 and next B. Okay. First selection line. This is selection line. One tick binary 0. Okay. This is I0 and this is I1. Okay. Like that I am using AND gate. Okay. For the OR gate, what is the OR gate? I0 equal to B, I1 equal to 1. Okay. For OR gate, so A is the selection line and B. Okay. So B, if you see, what is B? I0. Okay. I0, I1. Okay. I0 is B and I1 is 1. Okay. And similarly for XOR gate, if you see the XOR gate, what is XOR gate? I0 is B and I1 is B bar, no. So see here, XOR gate, XOR underscore gate, this is A is the selection line and this B and B bar, not of B. Okay, not of B. This is bitwise operator. Okay, not of B. Okay, and next NAND. So in the NAND, what I got? See here, in NAND, I0 is 1 and I1 is B bar. Okay, so I0 is 1 and I0 is B bar. Okay, so like that I can write for NOR, XNOR. Okay, XNOR, I will get B and B bar. Okay, end module. Okay, so this is nothing but my RTL code. Okay, so next I need to write the test bench. So how to write the test bench? I am using for loop. Okay, so I am using for loop. So here you see, by calling that functions. Okay, so module, this is the my test bench function tb underscore gate using mux reg a comma b where and underscore gate. So whatever the inputs are there, that I need to initialize for as a reg. Whatever the outputs are there, I need to initialize for wire, and I am instantiating. Okay, I am calling, that means I am instantiating that function. So that instantiating connection by what? Connection by name. Okay, so connection by what? Name. Okay, so connection by name. So whatever the design inputs are there, those are the outside the bracket. Whatever the test bench inputs are there, those are inside the bracket. Okay, and next I am initializing the integer I, initial begin, dollar display. So I can see in the TCL console also. Okay, or log file also I can see whatever the outputs of AND gate or gate also I can see for different combinations. Okay, and I need to see the combinations like I equal to 0, I less than 4. I am using a loop function, and I equal to I plus 1. Okay, I plus 1. So in the Verilog I need to use I equal to I plus 1. I am using concatenation operator, that is a comma b 1. Okay, a comma b equal to I. Okay, and dollar display. So for after one time units I need to display this values of this and end, and I need to finish the simulation, dollar finish end and end module. Okay, so this I will execute. 1 second. Here I will create one project. Okay, I'll create one project in Xilinx Vivado. Next, so okay, if this function is there, once I need to see. Okay, anyway I'll create new. Next, I will change. Okay, this path, this is the path. Okay, next, I'm creating the projects. Okay, what is that project? All gates underscore mux. Okay, all gates underscore mux. Okay, next, okay, finish. Project is created. Okay, project is created. Okay, so module name is same thing. So module name, in this I need to use this module name. Okay, so that module name, here I am using this module name, all gates mux. Okay, this I am copying and I am keeping this all gates using MUX, gates using MUX. Okay, yes, yes, here you see. So this is created. Okay, so this is created. This program just I am copying in this. Okay, where whatever in GVim is there, that I am copying. So this one I am copying. Okay, so copy this, just paste in this. Okay, save this. Okay, save this. Okay, it is created. Okay, after that I want to create the simulation file. No, so go to simulation, add this. Okay, next create simulation file. So what is my simulation file? This is simulation tb underscore gate using MUX. Okay, just copy this and paste this. Okay, finish. Okay, so I want module name also same. Okay, yes, yes. So simulation file is created. Okay, this is tb underscore. So just whatever the test bench is the I told, just copy this. This is test bench, no, not this is design. This is test bench file. Okay, this is the test bench file. Just copy this, and just paste this. Okay, next. So it should be connection by name only. Okay, I'm instantiating connection by name. Okay, save this. Okay, it has been saved. Okay, after that I want to see the circuit, how the circuit will be there. So open the elaborated design. Okay, open the elaborated design. Okay, so I want to see the netlist, how the netlist will be there. Okay, I want to see, reading the netlist. See here, this is the netlist. Okay, so can you able to see? So that means here based on this AND gate. Okay, so what is the AND gate? AND gate you are getting for I0 and I1. Okay, I told the AND gate, no. So what is the AND gate? For the AND gate you need to give 0 and B, no. So you see 0 and B, so that is I0 is 0 and I1 is B we are getting. Okay, I1 is 0. See here, it is giving to the ground. Okay, one signal is 0, another signal is B you are getting. Okay, and another, this A bit is what? Selection line. A is given as a selection line for all the muxes. Okay, and so here this mux followed by inverter you are getting NAND gate, and this mux followed by inverter you are getting NOR gate, and here you are getting XOR gate, and the mux followed by this inverter you are getting XNOR gate. Okay, so this is elaborated design. So I want to see the simulation part. So run simulation, run behavioral simulation. Run simulation and run the behavioral simulation. Yeah, see here. So in the TCL console also you can get the output. See here. This is the output. Okay. For AB, for different combination, what is the output of AND gate, OR gate and NOT gate? Okay, and NAND gate. Okay, so what are this? What are this? You can see. Okay, you can see this one. Okay, you can see. Okay, these are the outputs. I can see the simulation part also. Okay, so this is the simulation part. Okay, and different possible combinations of input. I given the for loop, no. So different possibles of inputs. So what are the outputs of AND gate and OR gate? Okay, you can see the simulation in QuestaSim also. Okay, same simulation. You can see the QuestaSim, but you need to use some commands. Okay, so this is about basic thing. Okay, basic simulation. So if it is 0 0, what is a AND gate, OR gate, XOR gate? So 0 0 means NAND gate 0, NOR gate 1, XNOR gate 1. Okay, and next if it is 0 1, what is the input? OR gate is 1. Okay, 1 0 1 1, like that you can analyze. Okay, so this is all gates by using all gates using 2x1 MUX. Okay, and next this one I can implement in QuestaSim also. QuestaSim also I can implement, but before that I will tell you this buffer, no buffer I told you, no, this is buffer. Okay, this is buffer, RTL code for buffer. Okay, this is the RTL code for buffer. Font size 16. Yeah, see here, module buffer inverter all gates. Okay, input wire A, output wire buffer and buffer or buffer XOR buffer NAND. So this is for buffer, and this is wire inverter and inverter or inverter NOR, like that. Okay, so for AND gate, buffer is possible, no, for buffer is possible, but inverter implementation AND gate and inverter is not possible, but we'll see. Okay, so whatever I told, that means for AND gate OR gate buffer is not possible, and for NAND gate inverter is possible. Okay, so NAND gate inverter is possible, like that. I can write the program, and this is for I'm using data flow modeling and assign, and with the expressions I'm writing. Okay, and this one is test bench TB file. Okay, so in TB file what I need to do, I need to consider the inputs as reg and outputs as wire. Okay, I need to instantiate connection by name. Okay, I need to initialize integer initial begin, and I want to display all these values, and I'm using for loop. Okay, and I less than to I equal to I plus 1, a equal to I, and I'm displaying this. Okay, and dollar finish means end of the simulation. This also I'm doing. Okay, just to file, so this close this simulation part, just close this, close the elaborate design. Okay, file, project, new project. Okay, here itself I can add. Okay, all gates here itself I can add. Okay, so I'm adding the source file, create the design, and next create the file. What file name I can give in this gates using MUX I'm closing. Yes, TB, this is also TB using MUX. Save. Okay, see here this buffer, no, so I'm giving the design name as what, buffer inverter all gates. Copy this, and just I'm giving the design name. Okay, finish. Okay, so design source is created. Okay, buffer inverter design source is created. If I want to see the elaborate design, set as top. Okay, you need to set as top. This code is there, no, this code I'm copying. Copy this. Okay, just paste in this, save this. Okay, and next TB file. This is TB file. Copy this. Okay, and one before that I need to create the TB file, no, just this one you copy this. Okay, go to simulation file, add simulation file, add, create, okay, finish. Okay, yes. Okay, simulation file is created. Which one is buffer, TB buffer, this one is there, no, so this is created. So just copy this code, which one, TB file, you copy this code, just paste in this. Okay, save this. Whatever the simulation file I want to see, so right click and set as top. Okay, so different designs are there. So whatever the simulation part I want to design, so here you will get 3 dots. So 3 dots means it is top module. Okay, this way it will be top on. Okay, so suppose if I want to see the MUX, so right click. Okay, set as top. Okay, you need to make set as top. Okay, so I want to see the elaborate design, so elaborate the design. See here, this is buffer, buffer and inverter by using different gates. Okay, so this is AND OR. Okay, XOR. Okay, inverter and in buffer NAND, buffer NOR, buffer XNOR, buffer NAND, buffer NOR, inverter NOR, XOR, inverter XNOR, inverter OR, like that. Okay, this is the elaborated design, and I want to see the simulation. So run run behavioral simulation. So I can see the TCL console also. I can see here. So like this is buffer. Buffer means what? Whatever the input is there, you are getting this buffer. Inverter means just opposite. Okay. So inverter, inverter we are getting. Okay. And for one also, buffer means one we are getting. And for inverter we are getting these values. Simulation part you can see that same outputs you are getting in the simulation part. Okay. So you can see. So this is buffer. Okay, buffer and inverter for different values. Okay, for different values of a and b. So a is 0 means we are getting different values of buffer and inverter. Okay, for a is 1 we are getting different values of buffer and inverter. Okay, so like this we can implement this all gates by using MUX, and how to implement this buffer, only buffer. So this one, so is buffer is possible for which gates. Okay, from here itself we can design the buffer and inverter. Okay, so this is about this session, today's session.